Next, we'll hear from Full Cycle Bioplastics.
Imagine going to the grocery store and the bread, beans, or pasta that you pick up comes in a bag. But instead of traditional plastic, that bag is made out of food waste. To you, there's no visible difference in color, clarity, food freshness. It's just a bag. And when you're done with it, instead of throwing it in the trash, you put it in your compost bin, where it'll be turned into something else. That's the circular economy. That's what we're working towards. The system we have now is more linear. We use energy, water, and labor to produce food, and in the US, we waste 40% of that food. It's a ton of wasted resources, and unfortunately, that's become the global norm. Oil-based plastic pollution and organic waste generation and landfilling are huge drivers of climate change. We need to change our mindset about materials production and waste management. The take, make, waste model doesn't work anymore. Luckily, we have a circular economy solution that addresses waste, pollution, and climate change. My name is Delane Mayer, and I work with Full Cycle Bioplastics, a California-based biotech company whose patented IP turns organic waste into a non-toxic, compostable plastic alternative called polyhydroxyalkanoate, or PHA. PHA-based plastic is fully customizable to its intended application, and it degrades harmlessly in the natural environment if not upcycled into virgin resin. The full cycle process has 4 key steps: waste collection, anaerobic digestion, where waste is converted to volatile fatty acids, or VFAs, aerobic PHA growth, where we fatten the VFAs up, PHA production, where bacteria convert the VFAs into PHA and we extract it, and from there, a PHA-based product is made, and ideally at the end of its life, it's upcycled back to step 1. No matter how mixed that initial waste feedstock is, our VFA intermediate is homogeneous. Our end product, our base PHA, will be the same no matter the diversity of waste put into the system. Full Cycle's PHA is the most cost-effective in the market, thanks to unique technological advantages in our patented process. Other bioplastics manufacturers rely on food source feedstock as a critical input. They grow corn, soy, or canola, employing agricultural systems that aren't cheap and that have a big land, water, and carbon footprint. We source waste that would otherwise be landfilled, thus reducing methane and carbon emissions and dropping our costs. Our PHA is different too. Our PHBV is a tailorable comonomer, and we can replace a wider variety of traditional plastics with it. Our diverse feedstock sourcing allows us to generate valuable precursors that are expensive to produce commercially from synthetic or food crop feedstocks. Our PHA gives the consumer the widest application range biopolymer. And thanks to our feedstock sourcing, Full Cycle offers the lowest cost, lowest carbon alternative to oil-based plastics available in the market today, bringing the circular economy well within reach. We're working with some of the biggest food manufacturers in the world, brands you probably have in your cabinet and fridge right now, to replace the plastics in their supply chain with food waste from their facilities. We've proven this concept at our successful commercial demo site in Mountain View. Here, we take 400 pounds of food waste a day generated from an assembly kitchen and turn it into PHA. At our on-site analytical lab, we evaluate the process and execute research for clients. This revenue-generating research is part of our business model. We analyze a partner's waste for feedstock potential for PHA production, or we examine plastics currently in use in a partner's supply chain and develop PHA with matching specs to replace it. There is so much demand for this research that we have to build an additional facility. The more research we do, the more we de-risk commercial scale partnerships. So we're developing a fermentation warehouse, a state-of-the-art and first-of-its-kind research facility. This warehouse of bioreactors will produce a variety of base PHA resin types to advance R&D, IP development, and commercial traction. Additional material production and R&D capacity will allow Full Cycle to more effectively engage large clientele interested in purchasing PHA. We'll advance from TRL 8 to TRL 9 as we commission our first licensed facility in New Zealand and develop a commercial scale facility in California. We do this work thanks to an amazing team of dedicated material alchemists, bioengineers, business developers, and tech wonks who are all driven to catalyze the circular economy. Full Cycle's co-founders and co-CEOs, Dane and Jeff Anderson, brought Full Cycle into force in 2014, moved to address the plastic pollution they experienced while surfing. Dane is an inventor and engineer specializing in automation, biological wastewater treatment, green chemistry, and scaling technology from lab to commercial scale. Jeff is an environmental engineer whose graduate work focused on the economics of PHA production. Full Cycle has since expanded to a team of 35 and counting, which is good because our pipeline includes $30 million worth of potential projects. Our business model includes two funded research pathways: feedstock feasibility studies and PHA-based product development, as well as technology licensing. Feedstock and waste providers who generate or manage large volumes of waste can turn their waste cost into a sustainable revenue stream by turning that waste into PHA. We first engage providers in a feedstock feasibility study, which characterizes their waste as potentially viable feedstock and provides a go-forward plan for commercial-scale waste offtake opportunities. For organizations looking to co-develop PHA-based products, Full Cycle will work with partners to develop a custom PHA copolymer with the aim of displacing a plastic currently used in their supply chain. This helps companies achieve sustainable packaging goals, differentiate their products, and de-risk their supply chains. Lastly, technology licensing of Full Cycle's IP helps scale PHA manufacturing. Licensing Full Cycle's tech helps meets the demand for PHA, increase revenue for Full Cycle and licensees, create high-value sustainable products, and addresses the local and global impacts of climate change. Ultimately, we can partner with anyone who produces waste or who wants a bio-benign alternative to plastics in their supply chain. This business model has been well received by investors. In early 2021, we raised a $2 million safe note from angel investors, and at the end of April, we finalized a $5 million safe note from a private equity firm. We're in the process of finalizing our $20 to $30 million Series A round now, too. This funding will go towards our R&D fermentation warehouse, where we'll conduct more paid research, our California commercial facility, and our New Zealand licensees facility, all of which will help grow the PHA market. The global plastics market was $450 billion in 2019 and is expected to grow up to $750 billion by 2028. Within that, Full Cycle sees a $270 billion market opportunity to disrupt both the traditional and bioplastics markets. Currently, demand for PHA is so huge that one of the larger PHA producers in the world expects to be sold out through 2024. There's a lot of room in the market for emerging biomaterials manufacturers. Terrestrially, we're scaling up to meet global demand, but we're interested in scaling down too. Beyond Earth, PHA's tailorability to use specification and end-of-life target makes it a unique and valuable material in space. PHA has the potential to enable circular product development on the ISS and lunar settlements. Our process could produce PHA-based 3D printer filaments, PHA protective padding for sensitive equipment to survive launch, or replace LDP food packaging. Our technology could even be designed to transform human refuse into a PHA-based material for construction. In our process, there are no hazardous byproducts or combustion risk, and even during extraction, we use bioprocesses to purify the polymer, so it's a benign process. We're developing automation on the analytics to ensure quality, and while we currently rely on technicians, our future system will be autonomous. Anaerobic digestion has and should be researched for long-term lunar missions as a solution for waste management, fuel generation, and manufacturing in space. But let's get one thing clear. This planet needs the circular bioeconomy to succeed. We need all kinds of biodegradable PHA in the marketplace. But unless NASA is planning to ship up canola, soy, woody biomass, or some of the other feedstocks required by other PHA manufacturers, Full Cycle's technology is the only waste to PHA option in space. We're interested in continuing the conversation to discuss replacing plastics in NASA's terrestrial supply chain, as well as supporting Artemis, Gateway, and beyond. The circular revolution is here, in space and on Earth, brought to you by Full Cycle.
All right, thank you very much. So do we have any questions? All right, Paul, go ahead.
First of all, very nice job. Really appreciate it. Can you tell us a little bit about the feedstock, the qualification of the feedstock that you use for your particular process?
Yeah, so when we are identifying potential feedstock, we do that through.
Delane?
Hi, can you hear me?
Yes,
I can hear you, Delane.
Okay.
I don't think Paul can.
Yeah, we can.
Paul, are you able to hear me?
I think he's having network issues.
Okay, well, I'll answer the question anyway and hope that he can watch the recording. The way that we look at feedstock optimization is through a feedstock feasibility study. So this is typically about 6 months long. Dane Anderson, who is one of our co-founders and co-CEOs, could get a little more into the technical details of that. But what we're really looking for is PHA yield.
Rob?
So
Question.
sorry, I'm getting some feedback maybe from Paul.
Yeah, I think
we're
Paul.
looking.
Robin, could you mute Paul while Delane finishes answering for now, and we'll have Paul go back and listen.
Mm-hmm.
Sorry, I'll start again. So in a feedstock feasibility study, that's about a 6-month-long process that we engage with with a potential client to de-risk commercial scale opportunities. So what we're looking for there is PHA yield potential, and that's what helps us inform how we want to step forward in the process and what kind of products are possible to be made with the feedstock that's in question. So with that, I will turn it over to Dane Anderson, who's one of our co-founders and co-CEOs, to talk a little bit more about the VFA optimization process.
Yeah, absolutely. Thanks, Delane. And great question. So we will do initial characterization analysis to understand essentially the complexity and characterization of those feedstocks, be it proteins, starches, carbohydrates, fats. And then we'll do targeted reactions that skew which intermediates are produced in the breakdown of those processes. From there, we can predict what polymers will be made based on our previous data, but then we'll also go through and produce the range of polymers that feedstock supports. So those characterization efforts really get us through the entirety of the yield and quality issues with any given feedstock to any given polymer, and allow us to know if it's a complete solution or if it should be supplemented or augmented in some way.
Thank you. I understand. Thank you.
All right, Alex.
Hi, again, great presentation. I'm really excited about your technology, not least of which because it potentially solves a really big problem with oil-based plastics. And my question is around that. I don't know if I missed this, but can you talk a little bit about the biodegradability profile of your plastic compared to oil-based plastics?
Yeah, happy to. I'll turn that over to Dane.
Got it. Thanks, Delane. Sorry, I'm struggling with buttons today. Yeah, so the biodegradability of PHA, or specifically our PHA, when compared to the petroleum plastics we're trying to replace. PHA is naturally found in the environment, especially our PHA. We don't use genetically modified organisms. The human biome actually has bacteria that are able to produce and consume PHA. So those enzymes are readily present. The timeframes, so we have not currently certified ours for compostability or the other pieces, but PHAs of comparable chemical compositions are certified as such. The timeframes, it really depends on the environment in which you put that PHA to degrade. On the shelf, it can last 15 years and be totally fine and still contain what it was meant to contain. But when it's put in a bacterially active environment, bacteria can then start to break it down. So that's moist with growth nutrients like nitrogen and phosphorus. And in those various environments, be it soil, ocean, an anaerobic digester, or a compost pile, the degradation time can range from about 2 weeks to a month to all the way up to about a year and a half if you've got a thick piece in a cold ocean with very few nutrients. But in comparison to petroleum plastics, that's night and day different. You're still watching our plastic break down in real time, whereas the others have, almost infinite life. Although, even as things break down, the more surface area our polymer gets as it breaks apart, the faster it will degrade. So there's an acceleration in the degradation, and there's no harmful microplastics that are produced, right? Again, even in our reactors, we produce and consume PHA readily within hours every day. And petroleum plastics, on the other hand, as they break down and start to break apart, you do have this toxicity effect of those microplastics, which are only getting more dangerous as it continues.
That's great. No, thank you. That's very exciting.
All right, Zach.
Hi, guys. Great presentation. Unfortunately, I know a lot about this topic, and I won't tell you why today, but maybe tomorrow we can talk about it. But so I heard you mention that your process doesn't use any GMO organisms. That's really cool and interesting. And I heard that you've not yet certified your product by any of the sort of governing standards. So to help me understand kind of where you are in your product development, have you yet determined your PHA is food safe? I mean, kind of like, where are you in terms of that testing and trialing?
Yeah, absolutely. So I'm actually trying to kick off our FDA approval process. We're hoping to have that by the end of this year. It takes about 4 months for the FDA to approve an application once it's submitted. So we're still in the legal back end of that now, but all of these are in the pipeline, including biodegradation and also a bio-preferred certification. But Dane, if you'd like to speak any more to that, feel free.
No, I think you nailed it. Yeah, we're pursuing them now.
Okay. And are you experimenting with both rigid and flexible plastics in terms of, form factors?
Absolutely. Yeah, we've done a huge amount of targeting films, which, we must be masochists because those are sort of low margin, high performance applications. But we started with some difficult stuff, and we've been essentially developing grades along the way. So the films has been our main starting point. We've also done rigids. Rigids are actually a bit easier with PHAs, and we're pursuing fibers and filaments. We're pursuing all kinds of applications at the moment.
Just to show you some film that we have on hand. So 2 samples that I keep in my living room for moments like this.
And my next question was going to be around transparency. So, and you kind of answered that with your sample there. So yeah, look forward to talking with you more.
Thanks.
We can share war stories.
Very cryptic, Zach, but I'm excited to hear it.
Okay.
All
Thank you.
right, Chandra.
Great presentation. I think it's really exciting technology that you guys are working on. You mentioned the use of a bioreactor for production. I'm wondering, what are the waste byproducts of that process?
Great question. Delaney, would you like it?
All yours, Dane.
Okay, no worries. Just wanted to give you the chance. The waste byproducts from our reactions are really just bacterial respiration of CO2. We don't run at high temperatures or pressures. There is some water evaporation, but all of those can be recaptured and reused in a closed system. At the end, there is, of course, a treated gray water effluent, which essentially has a bit of salinity in it. It has a bit of residual nutrients, but also that can be repurposed back into the front of our process to aid in the hydrolyzing of new incoming wastes. So there's really not a crazy residual left. Once we extract the polymer from the cells, there is a cell mass residual, and that becomes a bit of a bank of some of those growth nutrients, right? It has a lot of those proteins left over from the biological cell mass, and that nitrogen and phosphorus can come back in as if it were food waste and be recaptured again.
So I'll follow that on with how much CO2 is produced.
We lose about 20 to 30% of the carbon incoming as CO2 just based on what we call the bacterial tax. It's the cost of doing bacterial business.
All right. Thank you much. Rich.
Thank you. I was just wondering because there's a lot of difference between making a hydrocarbon fuel out of, say, corn or corn stalk cellulose. So I'm thinking that maybe there's a difference like you're producing in the different PHAs that you're producing. And I was wondering, on the basis of your choice of which PHA you want to make, is there a big difference or delta in your energy inputs that you require between those? I mean, is there one that's more energy efficient than others?
So Delane, I keep stepping on you. I would love to give you the chance. Go for it.
Go ahead, Dane, please.
Okay, apologies. Yeah, Richard, great question. Let me first explain the range of PHAs that we can make easily from anything. And this is sort of one of the key pieces of our technology is we make a PHBV, that's the 4 and 5 carbon monomer. That is naturally produced in nature. It's what comes out the most. And it can be made from almost any feedstock because it's built from the short chain fatty acids, which are the anaerobic breakdown products of almost anything. You can take fats to that, you can take proteins, you can take sugars, all to those short chain fatty acids. So what that becomes is the lowest common denominator for PHAs at all, right? That's how you can use mixed microbial consortia to do it, because you don't have to rely on anything taking a complex substrate like an oil, like a seed oil, and making a specific monomer continuously, right? Like when we shift from different PHAs, we're really shifting up and down the co-monomer composition of PHV with a backbone of PHB. There's not much difference in the performance of creating one BV composition versus another BV composition. So when we say we can make all kinds of different PHAs, typically we mean everything on the spectrum of PHBVs.
All right. Thank you. Next up, Mark.
Hi guys, thanks. My question is around the potential for commercialization. So if you could just give some rough order of magnitude for your planned commercial plant in California, or maybe your licensee's plant, rough numbers of how much raw or processed feedstock you're taking in, how much that generates, generally how many acres is one of these facilities. Just trying to think, is this something that we can deploy worldwide in large scales to really make a dent?
Yeah, we definitely hope so, and that's what we're banking on. So at least for California, we're still negotiating land lease at the moment, but that's about a 1 to 3 acre facility for a 150 to 200 incoming wet tons per day facility. And I'll let Dane speak a little bit more to how New Zealand is being developed.
Yeah, absolutely. So I act as the CTO. So we're limiting technology risk and scale as we go. So New Zealand is actually scaling in 2 phases. The first of which is a 10x on what we've got at our demonstration facility, and that's about 25 wet tons a day of input. So that's the waste feedstock coming in. And we are getting roughly a 5% yield. So wet weight to dry weight PHA. That is essentially a proof point and a demonstration in that market, and we're then expanding that to 200 tons per day of wet waste incoming, and expecting a similar yield. Although the yield for our process is very much dependent on the feedstock, right? If we took pure sugar, we would get a much higher yield, but when you're bringing in something that's primarily water, we're not converting water to PHA.
And I'll add to that too, Dana hinted at it, but these are modular facilities. So that will impact the land requirement, it impacts the feedstock required up front. And so if there's a customer interested in a smaller scale facility, but with a high PHA yielding feedstock, we're interested in that too.
And Mark, you didn't ask this directly, but to speak to the goal of that question, at least my perceived goal of your question was how big can this go? Can it be implemented globally? We get amazing economies of scale in going bigger. So when we target sites that are 1,000 tons per day, 2,000 tons per day of incoming organic waste in a consistent fashion, those economics are fantastic. And so, what we're targeting right now is sort of the minimum viable for economic returns, but there are tons and tons of opportunities to go much bigger. And the economics drive the deployment and expansion of the tech.
Great, thank you.
All right, thank you very much.